And now that we introduce control NOT gate, we have a set of gate that allows us to approximate any unitary operation on any number of qubits with any precision of our choice. So we can construct a universal set of gates. So that means that picking only gates from that particular set, we can construct by concatenating those gates any unitary operation with any precision of our choice. It's a beautiful result, right? It says that we don't have to, in the process of building quantum computer, quantum logic gates, we don't have to play with a huge number of gates. There's just small number of components that is enough to construct anything that we want. So that's a good moment to look what kind of classes of gates we have and which of them are universal. So first of all, a important class of gates that we already discussed in the context of a single qubit is a set of Pauli gates. For n qubits, we are talking about n-fold tensor product where you apply a given Pauli gate to a given qubit. So for example, you can think about applying x to the first qubit, applying the identity, which we include into the set of those gates, to the second qubit, applying the z operation to the third qubit, y operation to the fourth qubit, and z to the fifth qubit. Now I have included also the prefactor like +1, -1, plus I and minus I, just simply to make sure that we stay, that the whole thing has a group structure, because if you multiply two Paulis, you may get if you multiply z and x, you may get something like -I_y, for example. So you in order to just stay within the group, you have to include those factors. So the Pauli group can be generated by concatenating essentially x and z gates. So if you have ability to apply x and z to any qubit of your choice, then together with identity, just that's a mathematical addition here, then you can construct any element of the Pauli group. So clearly this might be interesting group, but we can see right away that the Pauli group offers us only a finite number of operations, so we cannot clearly hope to approximate any unitary on n qubits with this set of operations. But nonetheless, it is a very important group, important class of gates that you will see again. A slightly larger group is what we call the class of Clifford gates. Again, remember Clifford. In the single qubit case, we were talking about the Hadamard gate, about the phase gate, all Pauli operations, of course. Now we are adding C0. So that's our Clifford group for n qubits. So we assume, of course, here that we have n-fold tensor product of Paulis, Hadamard, S, and we can just connect any two qubits with C0. So that kind of operations constructed from that kind of gates form a class, and then again you can see that this sort of this mathematical structure forms a group again, which in fact can be generated by the Hadamard, the S gate, the phase gate, just to remind you that this is equal to 1I 0 0 and C0 with possible prefactor I. So you can see that's enough, because the Hadamard and S operation can generate all the Paulis. So that includes all Pauli operators. So this sort of set of gates is again quite interesting and useful. But for example, for one thing, we know that the set of gates like the Hadamard and control NOT can generate quantum entanglement. So we can see that there's much more power in the Clifford class than in the Pauli class. Pauli gates being n-fold tensor product of single qubit gates cannot generate any quantum entanglement. For that you need this extra addition, you need this control node. So Clifford gates generate interesting quantum states, there's no doubt about it. But again, this is sort of a, you can see that it's just for n qubits is a finite number of those operations, and again you cannot just hope that concatenating Hadamards on any qubit, the phase on any phase gate on any qubit on C0, that you're not going just to explore the whole vastness of unitary operations on n qubits. However, what is interesting is a tiny addition to the Clifford group, namely taking Clifford and adding anything that is outside this group. And the most common, the most useful choice and the most studied choice is adding the T gate. So we are now talking about the class of gates which we called Clifford. So you know all the Clifford gates, right? Plus pick up one that is not Clifford, and the canonical choice is the T gate. Just remember that T was phase shift by pi over 4. So that's your T gate, and this class Clifford plus T can be generated by the Hadamard, by the T gate and C0 gate. So that means that, well, what then the claim is that this particular set of gates is universal in a sense that by adding the T gate, we have now all the richness to explore the whole class of unitary operations on n qubits, and we can actually, by concatenating those gates, we can approximate, we can approach any unitary operations on n qubits with any precision of our choice. And it's in particular this the construction on a single qubit that is truly beautiful, involves in fact using gates T, H, TH, and SH, TH, S dagger. So that would be those gates are quite often called TX. Sorry, that would be TZ, TX, and TY. In the language of the Bloch sphere, TZ, which is a T gate, is rotation by 45 degrees about the Z-axis. TX is rotation by 45 degrees, but about the X-axis, and TY is rotation, of course, by 45 degrees about the Y-axis. So it's a beautiful construction due to Matsumoto and Amado. They managed to show that when it comes to at least single qubit approximations, you can actually achieve concatenating TX, TY, and TZ with any Clifford operation is actually enough to approximate any unitary on a single qubit. So you can think about it this way, that if you know that Clifford walks on the Bloch sphere are rather boring because they visit only 6 points on the Bloch sphere. But Matsumoto and Amado walk actually are much nicer because then you start walking much denser, much more complicated, much more interesting, because you start visiting every single point or the neighborhood of every single point on the Bloch sphere. So that means if you sort of make a step by equivalent to 45 degrees of rotation about X, and then 45 about Y, and 45 about Z, and say 45 about Y again, and so on and so forth. So you you concatenate tx, ty, tz in any order, then you actually explore the whole vastness of the Bloch sphere. And having the C0 gate allows you nicely to sort of spread it over many qubits that you have, so that you can we are not going to show this, but the statement essentially is this set of gates allows you to approximate any unitary operation with any precision. Now you may ask, okay, well, how hard it is? How does it scale with n, for example? How does it scale with precision? So there's a good news and the bad news. The bad news is that any generic unitary operation is it's difficult to approximate if you increase the number of qubits. So your number of gates needed for the whole thing from this set grows exponentially with n. But the good news is, well, when it comes at least to precision, then it's just Pauli logarithmic in 1 over epsilon. So remember the Solovey-Kitaev result. So when it comes to precision, fine, we can fix the number of qubits, and then if you want to approximate a given unitary operation with a little bit more precision, then it's you don't have to work that hard. You may just maybe repeat the whole sequence 4 times, and then again, so substitute for every block another 4, and so on and so forth. So that means that your work, in order to increase the if we sort of make this epsilon smaller and smaller, so one of the epsilon grows, the effort in terms of number of gates needed is not growing that rapidly. It's just like a logarithmic function, a Pauli logarithmic function of 1 over epsilon. But with n, unfortunately, it's just if you increase the dimension of the Hilbert space, if you add another qubit, the dimension grows exponentially. And unfortunately, to just explore the whole vastness of this Hilbert space, the number of gates also grows exponentially if you want to just approach any unitary operation with any precision. But the good news is that we don't have to study all kind of complicated interactions as long as we understand the Hadamard, the control node, and the T-gate. So the Hadamard, the phase shift, the control node, as long as we sort of can construct those basic primitives, then we can just do pretty much whatever we want. And that's how we are going to build quantum computing devices, and how we are going to construct circuits that do interesting computations.